Well, good morning, everyone. Beautiful day out there, especially in Mississauga, Ontario, or Missing Saga, as I like to call it. Thank you for attending. Really appreciate it. For episode 4, Control Valves, Last Chance at Good Control. My name is 𝗦𝗨𝗕𝗦𝗬𝗓. I am the Process Optimization Specialist for Lakeside Process Controls. So a bit of guidelines before we start. Your microphones are off. There will be no verbal communication. I encourage you to ask questions through the Q&A box. You can actually ask questions. You can also ask chat with me if you want to. So your questions, you can ask your questions at any time, and will be answered. Actually, it will not always be answered at the end of this session. I actually have Tim Jentz, who is our valve specialist. There he is right there. You can see him. And Tim, perhaps you can maybe talk about what you do and what your specialty is at Lakeside for a few minutes.
Hello all. Yeah, my name is Tim Jentz. I'm a valve specialist here at Lakeside as well with 𝗧𝗏𝗦𝗧𝗔𝗬. And my background is I've been around the Fisher product line for 35 plus years, spent 5 years at the factory, and then the remainder 30 plus years working here at Lakeside as a valve specialist looking after the Fisher product line.
Awesome. Thank you very much, Tim. Tim will be actually answering some of the questions as you type them in. He will type them back. And at the end of the session, I will go through all the questions and the answers. I want to make sure that all the questions are answered. Oh, there we go. There is a 10-second time delay from the moment you actually see, moment I speak to the moment you hear me. So 10-second time delay. So if light travels at 300,000 kilometers a second, that means I am 3 million kilometers away from you. And actually, this is where I'm broadcasting from. And this is my other colleague here. He's doesn't have a very good sense of humor. I try to make him laugh, but never seems to work for some reason. So your questions, like I said, are anonymous. Only I can see, or Tim can see who asked the questions. So there's no shame, nothing like that. Don't be shy. And that's at the end of the session. There's still not enough questions. Feel free to reach out to me via email or phone or something like that, and we'll make sure that we can answer. We'll make sure that we will answer your question. And this is my contact information: 𝗦𝗨𝗕𝗦𝗬𝗓@lakesidecontrols.com, and obviously, cell phone is the best way to reach me. This is part of the series of lunch and learns I've already done. This is my 4th one, and next one will be in June. We'll talk about that at the end. And these are all the series of, and these are all related to controls and process control, loop tuning, and so forth and so forth. As you see there, the actual subjects get a bit more and more sophisticated as we go along. I kind of built it that way. This is being recorded, so you will have access. If you want a recording or a link to the recording for this presentation, again, contact me and or contact marketing, and we will forward you the link. Therefore, if you want to look at it again in the future. Bit of safety moment right now, and this actually kind of touches me a little bit personally right now. I actually went to see a dermatologist yesterday, and I actually have a not serious skin condition that was caused by excessive sun exposure. So obviously, especially a day like today, and the weather's going to start getting warmer and so forth, skin protection is actually very important. Cover up, sunscreen, SPF of probably, you mentioned up to 50, and so forth and so forth. So obviously, be careful. Even if you're young, we'll all be young and stupid, but it kind of catches up to you later on in life. So be wary of this. Be aware of this earlier on in your life. A little bit about Lakeside. Founded in 1952, we have offices here in Mississauga, Guelph, Sarnia, Sudbury, Thunder Bay, and Winnipeg, and Port Elgin as well. And we actually work in all these industries right there. And I've worked pretty much in all of those industries myself. And Lakeside is part of a larger network. It's called the Emerson Impact Partner Network. There are 21 of them. And we all have our own distinct territories, and therefore we do not compete with each other. Sometimes we help each other out. You can see our territory number 9 is goes from the Manitoba-Saskatchewan border all the way to just this side of Kingston, and east of there is taken by Laurentide Controls all the way to the Maritimes, and west of us is Spartan Controls. There you go. And we're locally certified. We're the primary source. If you want to buy an Emerson product, obviously we are the exclusive distributor within our territory of Emerson products. We will know who to talk to if you have a specific application. We will know who to talk to at Emerson to get the proper solution for you. And this is kind of a terrible slide, but we sell a lot of stuff here. Like obviously on the instrumentation side, control valve regulators and so forth is what we're talking about. We also have our own control DCS platform called 𝗪𝗘𝗕𝗦𝗓. We actually have another one also called Ovation, primarily focused in the power industry and the water and wastewater. Project management, we do manufacturing, assembly, educational, and project and consulting services. So the idea here is we want to make sure that every time you have a deal, you deal with Lakeside, we want to make sure that it's a positive experience and that we're able to help you throughout your implementing your solution. A little bit about who I am. This is a pre-pandemic haircut you see there. I go in the field and go actually assist and tune control loops in the field for customers. We talk about how actually tuning control loops is actually the last thing you do. We need to have a good process, control strategy, instrumentation before loop tuning is effective. And also deal with advanced control. MPC stands for Model Predictive Control, and neural net as well. As a matter of fact, actually, I know there's someone out there in the crowd today where I'll be experimenting with a neural net to actually predict a lab value and hopefully be able to allow the operator, if we get good correlation, to allow the operator to make a decision before we actually get the actual lab value. So be very interesting. DCS alarm metrics. A lot of times DCS alarms as part of a DCS project is actually sort of the last thing we think about. We tend to set all the high alarms at 90%, high at 80% span, low at 20%, and low at 10%. And what we do, we don't put a lot of thought into it. When we start up the plant, we get a whole bunch of alarms, and two things will happen there. First of all, it's like, where's Waldo? If we have a critical alarm coming in a full alarm banner, good chance that the operator is going to miss it. And that's when bad things happen. And the second thing that will happen as well is the fact that the operator will get desensitized to these alarms and will ignore them. And again, bad things can happen. Most industrial disasters that occur will have some roots in poor alarm management. And that picture there is actually not a stock picture. It's a real picture that I took at site where someone, the alarm is going off all the time. So someone decided to put a steak knife in the silence button. I do have a couple of individuals that work with me. They don't work for me. Andrew supports me as much as he can, but unfortunately he got himself promoted, so he's a team lead now. He doesn't have as much time to dedicate. And Dean, I'm glad to see Dean is coming back from a long-term project as well, so he'll be able to help me out. And I do teach courses as well, basic instrumentation for operations course. That one is going to be, next one is next week. Cutoff day is today. And I do teach also process control techniques 1 and 2, aka loop tuning 1 and 2. Loop tuning 1 is going to be June 1st and 2nd. You can sign up on our website. And I also have a blog as well, where I talk about some of the stories I've accumulated over the 30 plus years. They're not super technical, and I'm trying to make them a bit humorous, but also I try to put a moral to the story as well. So, okay, so this is the thick of it here. What are we going to cover? talk about what is a control valve, the components of a control valve, different types of valve. We're going to talk about the CV curve and how it relates to the actual flow, valve sizing, backlash and stiction, and the NTEC valve spec. I'm not too sure if you have anyone. If you actually, the NTEC valve spec is actually, if you go to your handouts tab, you can download that PDF should you wish to. So what is a control valve? It's a device that will modulate flow. Now, we got to understand here, yes, we have level control valves, we have pressure control valves, temperature control valves, and so forth. But a control valve will modulate one thing and one thing only, and that is flow. It'll do that by varying the size, the aperture that of the opening within the valve body itself. And the more open it is, obviously, the more flow it will pass through. So the basic components of a control valve. So here we actually have the valve body itself. So you have the valve body itself. So let me see here. So the valve body itself there, that is actually where the fluid will pass through. In this example here, the fluid will actually pass through this way. And so therefore, the type of valve, the size of that body, the type of the body, and everything else will determine the actual flow characteristic. The actuator, obviously, is the muscle that will actuate that valve, be it linear. In this case, it's a linear valve, be it linear or rotary. And will therefore, we have diaphragm actuators, we get piston actuators, single acting piston, double acting piston actuators, and therefore you also have can have electropneumatic electropneumatic actuators as well, and electric actuators. And the positioner. Now, the positioner itself is really the brains of the operation. Now, we understand that electrical signal here that we have here, that's a 4 to 20 milliamp. I'm poor drawing here. Maybe I'll work on my new stylus. I've built myself a new stylus here. So the 4 to 20 milliamp signal. So if we go to 20 milliamps or 12 milliamps, which is 50%, so 12 milliamps, it's not working very well. Let me try it again. No, it's not working very well. Okay, I'll give it up. 12 milliamps is 50%. And I apologize for the poor handwriting here. I was trying to write with my finger. So the job of a positioner is to make sure that the actual position of the valve, the feedback coming from here, is actually matches the command signal that we send it. As the name implies, it will position the valve to where we tell it to be. If we did not have a positioner, if we told the valve to be at 50%, we don't know where that valve would be. And therefore, the positioner is critical to actual precise actuation of the valve. And based on where the valve position is and where we want it to be, it will then actuate the valve to make sure that that valve comes back to where it should be. And why do we do this? Why do we go through so much trouble with control valves to have the right actuator, properly sized, and a positioner? Is that the more precise and dynamic a control valve will be, the better control we will get. And based on that, then we'll be able to do all our tighter control, our target shift, and increase our profit margin, increase our production rate, decrease our costs, material costs, and energy costs. So right here, I'll pass it on to Tim. Maybe you can talk to this slide right here, and I will then click on it as you talk.
Thanks, Sylvain. So obviously, a good control valve needs to make sure that when it's designed, it has a number of good attributes about it that makes sure that it will respond to the control signal. So what are the three main things? Does the valve move? How fast does it move? And does it have the right gain? And I'll be careful with that word gain, because Sylvain will get into that a little bit later when he gets into the meat of his material. So obviously, when Fisher Controls, the manufacturer of the valves that we deal with, they do a lot of flow geometry testing using CFD and design modeling to make sure that when the flow goes through the valve, it's stable and there's no instability when the flow is going through the valve. Also friction, and I get a lot of questions from the field from different customers where they'll say, hey, what's good and bad friction? Well, friction, there's really not good and bad. Is basically what we need to understand is what is the friction in this valve, and making sure that it stays within a design parameter spec that when it left the factory, hopefully it can maintain that same friction. So at some point, if we're able to measure that friction, we're able to determine whether or not the increase or decrease in friction over time is going to have an impact on our control loop. And again, Sylvain will get into that. And ensuring that all the loss motion and what we'd call slop, I know that's kind of a slang term, but we want to make sure there's no slop in the control valve. And the other great thing, and I mean, Sylvain has talked about this already, but the positioner design is critical to make sure that when the signal coming from the controller, in this case, you know, Sylvain's talked about 4 to 20. I mean, we can have other control signals, foundation, field bus, profi bus, but the common one that everybody's used to is 4 to 20. Is that when that signal comes to the positioner, we want that thing to move. We want it to move smoothly and quickly and get there to set point and no oscillations whatsoever. Now, one little tidbit here, and you know, this is not part of this conversation, but if the positioner has the ability to be smart, and what we call smart, meaning that it has the ability to do some additional advanced diagnostics, then that's just an additional feature that's now been asked for in many of our new positioner designs now. And the common backbone that we use for smart is what we would call a HART positioner, HART, which again is not part of this conversation.
All right, great. Thank you, Tim. I always say smart is equal to heart. That's so it's always my saying there. And you'd be amazed actually how much diagnostics you can actually gain from these smart positioners. It's incredible to be able to how you can troubleshoot it, and you do it remotely. You don't have to be actually at the valve itself. I worked in the oil sands, and believe me, sometimes you want to troubleshoot a control valve. You don't want to go about half a kilometer, about 100 feet in the air at minus 40. It's not always the most pleasant scenario. So there are two types of valves. We have rotary valves and sliding stem valves, the two different types of valves. So this is a rotary valve right here. This is a very common bread and butter type of valve. It's a V-ball. And you can see here there's a bit of a V notch. It's actually the ball valve. It can be a bit of a misnomer because it's actually a segment of a ball. It's not a full-blown sphere. And the V notch there actually improves linearity. And this is going to be critical here. We're going to talk about this later on, talking about linear flow characteristics. Typically, the flow will actually, the ball will face the flow. And pretty much most of the cases, not all the cases, but most of the cases. And you can see here, we talk about flow through. If the ball or the valve is completely open, the fluid will pass straight through. So there's no tortuous path. So it's a very good high rangeability. A rotary valve is a butterfly valve is essentially a disc that will rotate and therefore change the surface area, open surface area, and allow more or less fluid to pass through. Now, you got to be careful here. I know Tim's listening to me right now. Is a traditional butterfly valve has a quick opening flow characteristics, and we'll talk about that later on. A quick opening flow characteristics. But we do have some other models. What we have is called a control disc, and there's an attachment. It's not an attachment. It's actually a modified disc that actually will provide more linear flow characteristics. And maybe, Tim, you can maybe add a bit to that if you want to.
Sorry, Savannah, I was typing, and you probably heard me typing. So you might want to repeat the question. I'm sorry.
No, it's not a problem. Not a problem. I can't multitask either. No, I was talking about the quick opening flow characteristic of a traditional butterfly valve. But we do have also something called a control disc that can provide more linear flow characteristics. I was wondering if you could add a little bit to that.
Sorry. So yeah, so the control disc is a design that Fisher has put into the shape of the disc, and depending on how it's modified, we can actually create a CV curve where it's actually equal percentage based on the shape of that disc. So it's not your traditional shape that everybody's familiar with. It's actually got, and I'll use the term, and I know Fisher sometimes doesn't like to hear this because it's not technically right, but they'll put a fishtail on it, and the tail will actually be on the upstream side of the valve. And as the valve opens, it actually creates an equal percentage flow, which Sylvain will get into, and that's actually a good thing because it allows for traditional applications where butterflies would go to actually be used in a wider range than a traditional one.
Awesome. Thank you very much. So sliding stem valves, as the name implies, where its actual stem will actually move up and down. So it's a linear valve. And right there is a trim. The shape of that trim right there will determine the flow characteristics. Now, what I'm showing you there is actually a stem-guided valve. But there is also a cage-guided valve. So maybe I'll go backward here. So glow valves are very good at good rangeability. We'll talk about that a bit more later on, but they can actually modulate from about 20 to 25% open all the way. They get good modulation range up to about 80% open. A lot of other types of valves no longer modulate at such an open percentage. So they're very, very good at modulating very wide range, as well as they can handle very large pressure drops as well. I've seen some where, especially severe service types of valves, where they can handle up to even 1,000 psi. They're very specialized, but they are specialized type of valve. But they are sliding stem valves as well. And as I mentioned, there's also a cage-guided valve. So what you can see there, inside that cage is actually just a cylinder plug, just plain old plug that moves up and down. And as it moves up, some of the fluid will start to come out through the actual characteristic, the opening there. And you can see the shape of that opening will determine the flow characteristic of the valve itself. So when you buy a control valve, it comes with a CV curve. It comes with a CV curve. So typically CV curves can be equal percentage, linear, and quick opening. And what I'm going to do now, I'm going to put a poll out, and I'll give you about 5 or 10 seconds to answer which one of the CV curves do you think is most common. Oh, it's coming. They're coming in. This is great. Thank you for participating. And it's a bit of a close race. So 44% said equal percentage, 34% said linear, 21% are saying quick opening. And you can keep on answering. And so thank you for participating. So actually the most common type of CV curve there is equal percentage. Now it makes you wonder why. I mean, don't I want a linear kind of flow response? I want to achieve a linear flow response, but you have to understand that as I open up my valve, the pressure drop across that valve will drop. And the formula that I'm showing you right here, that's a very basic formula. I mean, for different types of fluids, it gets a little bit more complicated. But the backbone of any kind of flow versus CV versus delta P relationship is right there. The flow through a valve is equal to the CV times the square root of delta P. And you can see here, you can imagine as I open up my valve, that there's obviously the opening gets bigger and bigger. There's less resistance. I will then lose less energy as the fluid passes through. Therefore, P2, the downstream pressure, will tend to go up. Therefore, the differential will tend to go down. Now, there's also another situation as well, especially for liquids where you have a pump curve. Pumps will each have a centrifugal pump, will have a pump curve. It can only deliver so much energy. And the more flow being generated, being pumped, the lower the discharge pressure will be. So you got a bit of a double whammy here. So therefore, that's why as the valve opens up, we know the pressure drop, the DP, will fall. And therefore, that's why we need sort of that extra kick as the valve opens up to compensate for that. And hopefully, we will have a linear flow response. That is our objective. So this is what can happen here. This is actually what happens when this is actual real data. And this data was collected back in December of 2018. What I want to show you here is actually this is a pump failing, and the pump actually is wearing out. So you could see here at 44%, in this case, I was getting 302 tons per hour of flow. And then in April, you could see now that I'm not getting less flow for the same valve opening. And then in May, even less. And so the issue was that obviously if we're actually operating right around here, we were no longer modulating the flow characteristic. In this case, because of the pump was failing, was wearing out, they were not able to actually modulate and control the drum level. In this example here, this is feed water, very, very well, because they were actually not able to modulate. So this is kind of similar to a type of valve that we're going to talk about in a minute. And again, this is the actual pressure versus flow curve, or flow versus pressure curve. And you can see the more flow being pumped, the pressure is actually dropping. And this is back in November of 2018. And then this is actually in May of 2019. So you could definitely see, if I flip back and forth, that the pressure, the pump is actually wearing, that curve is actually dropping lower and lower and lower. So I'm going to show you a bit of a demo here. So to kind of further that concept. So there's a lot going on here. Okay. So this is a simulation that I built. Don't get too excited about this. It's kind of a rough simulation. But what I've done here is I built a pump curve. So the bottom axis here is the actual flow. So this is a flow control valve. We're measuring the flow. We got our controller here. The faceplate is right here. The output goes to a control valve. The valve's at 10%. And right here, there's 37 PSI drop across that valve right now. And as the flow will increase, the actual discharge pressure of that pump will start to drop. Now, I can have two different types of valves here. Now, believe it or not, and I always found this kind of hard to believe myself initially, but a butterfly valve actually has a borderline linear CV curve. So as the bottom axis here you see is the valve opening from 5% to 100%, and that is a CV value on the y-axis. You can see here the green arrows is where we're operating. And as I start to open up this valve, let's say I'll go to 30%. 30%. So now my CV is increasing linearly, but my pressure drop, my pump discharge pressure is falling off the curve. And therefore now I don't have as much pressure drop across that valve. But since my CV curve is linear, therefore I'm not going to start seeing the same amount of change in flow. So, and I'll show you this a bit more in a minute. So here we go to 50%. And now I'm not still operating in this range. And now you can see I'm definitely falling off the pump curve. So let me show you this in a trend. So this is what I actually did earlier this morning. So the blue line you're seeing there is the output command to the valve. They're each 10%. So I went from 10%, 20, 30, 40, 50, 60, 70%. The yellow line is the flow feedback. And you can see here that I'm getting quite a bit of change in flow at the bottom end, but each subsequent bumps, I'm getting less and less flow change. And that's because my pressure drop, if I actually show you a bit more here, the pressure drop across the valve is decreasing and decreasing. So if I take a look at this chart right here, the orange line is the actual CV at that particular valve. And it pretty much matches the blue line right here because it's a linear CV. The pink line you see is a pressure drop, and I get large pressure drops at the beginning, but then as we're falling off the pump curve, we're getting less and less pressure drop. For an equal CV, I'm going to get less change in my flow. So now I can actually change this valve type to a V-ball, sorry. A V-ball actually has an equal percentage flow characteristic. So as I'm closing and opening the valve, if I go back to say 20% here, you can see here I'm not have quite a bit of CV actuation because I actually have quite a bit of actual differential pressure across. But as the pressure, discharge pressure decreases, this is where I need that extra kick, and that's why we use a equal percentage CV curve to compensate for the drop in pressure. So let me show you that again via the trend. So let me go back to here. And so I'm going to increase it. So once again here, we got the output changes the same. So we went from 10, 20, 30, 40, 50, 60, 70. And you can see the actual flow changes are not exactly the same, but they are a lot more linear than they were before. So let me maybe try to put both of them at the same time. So there you go. This is actual here, the butterfly, and this is the V-ball right here. And you can see here for a butterfly valve, again, if a butterfly valve is operating at probably 60 to 65% or more, you are no longer controlling. You're no longer modulating. Whereas a V-ball could go probably up to, we probably push it around 70% before it starts to give up the ghost. Okay, one more thing I want to show here actually is, and go back here now for this a bit more. This is the orange here is the actual CV as the valve opens up here. So let me set this up properly again. And you can see here for smaller openings, I get less CV change, but the more I open, the CV increases. Essentially, it's following the CV curve we just talked about. And therefore, that equal percentage is there to compensate for that drop in pressure, and we're trying to linearize the flow. Let's talk about valve sizing. So valve sizing is very, very important. So when you call up Lakeside, you say, I want to buy a control valve, we're going to ask you a lot of questions, from anything from what type of fluid it is. We'd like to know what the inlet pressure will be. We need to know what the outlet min, max, and normal flow. And based on that, based on a lot of other questions, we'll determine what type of valve and what size of valve should be. Now, I look at it from a control perspective. I look at it from something slightly different, from the process gain. Again, we're not talking a PID proportional gain here. So that's why I always kind of shy away using the term process gain. I rather talk about process sensitivity. And the process sensitivity is a ratio of a change I get in my process versus a change I made in my output. So this is the output command to the valve, and then I observe how much of a change I see in my process. And I talk about talk about this in the universal language of percent of span. And therefore, the process sensitivity, Kp, is the ratio of a change I got in my process for a change I got in my delta U. So therefore, what I'd like to do, for a properly designed control loop, Kp, your process sensitivity should be between 0.5 and 2.0. That means for a 1% change on my output, I want to see my process change between 0.5% of span to 2% of span. All too often, though, I'll go in the field and I'll do some bump tests, and I see my process gain could be 3, maybe 4, maybe 5. That means for a 1% change over here, I'll see a 5% change on my process. What do you think that means? Well, what it means is that if I do a small change, I get a big change in my process. The odds are, no guarantee, but odds are it means that valve is probably oversized. And why? What's wrong with oversizing control valves? First of all, you got a control valve that operates at 25% or less most of its life is likely to be oversized. And we're wasting a lot of horsepower across that valve. We may even probably end up wearing out that valve because the velocity of the fluid passing through is so high. But the one issue that is the biggest problem with oversizing control valve is that if I have a 1% problem on my control valve, and we'll talk about that in a minute, backlash and stiction, if I have a 1% problem here, translates into a 5% problem on my PV. And therefore, oversizing control valves can make small valve problems big problems on my PV. So back to our butterfly versus ball valve. So this is actual data that I collected off my simulation. So again, there's a lot going on here. So on the y-axis here, you got your flow, and on your x-axis, you got your valve position. And these are the step changes I made. The black line is the step change that I made. The red line is the process sensitivity of that valve at that particular point. And you can see here that for a butterfly valve, for right now it is a butterfly valve, is highly nonlinear, and that as more you open up, the process sensitivity gets less and less and less. Whereas a ball valve, I get a pretty close to linear response, and you can see as I'm opening and closing, the actual flow gain, flow sensitivity doesn't change all that much throughout that wide range. And that's something we want from a control perspective. We like things to be as linear as possible. It makes tuning more robust at a wider range. Therefore, that's why we want a more linear flow characteristic. Now, you heard me hint about valve backlash and valve stiction. Precise control equals good control. So a control valve needs to be precise, and that's why we talk about putting a positioner, a critical application, a component of the control valve to make sure that we actually will position that valve precisely. Now, control valves suffer from two major afflictions. One's called backlash or hysteresis, and the other one's called stiction, or sticky valve, a valve that hunts. So how do we actually detect? So when I go to a control valve, I want to do some bump tests, because that's how I'm going to calculate some process dynamics when I do my bump tests, and that's how I actually will use that information in my tuning. But also, I use the bump test to determine how precise the control valve is. So I typically start with 1% bumps. Now, there's two reasons why I do 1% one. So obviously one is to measure the precision of the control valve. And the other one as well, I don't know if this valve is oversized, undersized, or anything like that. And therefore, I start with 1% bump because I don't want to disturb the process more than I need to be able to measure my process dynamics. Believe me, I've joined the megawatt club once, and once is enough. Yes, I tripped 100 megawatts once, and not a pleasant situation. So here I go 1% up, 1% up, 1% up, 1% up, 1% up. Everything looks good. Now, backlash or hysteresis, the term are interchangeable, is due to mechanical looseness, mechanical slop, as Tim calls it, within the valve assembly. And the way that demonstrates itself is that when I now do a reverse direction, I will actually then not see any change in my flow. In this example here, I will have 1% imprecision in my control valve. And that 1% imprecision will have a direct impact on our ability to control. So I'm going to show you a video here. So let me set this up first. So what you see there on the right-hand side, you see two tie wraps. One tie wrap is actually attached to the valve stem. So as it goes towards the right, that is actually going into the valve body itself. It is a rotary valve. That stem then is mechanically coupled to the actual valve actuator, and that's where the second tie wrap is. And I use those two tie wraps to indicate the position, and it's patent pending, so you're not allowed to use that invention. So I'll play that, and you'll hear me in the background. I'm not sure if you hear me or not. Now they're moved together. Backlash is taken up. So at this point, the backlash is taken up. So I'll pause it right there. So the next thing is that the valve will start to close. I mean, the tie wraps will start going down. I want you to pay attention to the left tie wrap compared to the right tie wrap. Now it's going to go the other way before it actually engages. So as you can see here, there's probably, in this example, I would guess probably 6 or 7 or 8 degrees of backlash in this example here. And this was controlling a level control. It was actually controlling a very small, high throughput tank level. And they were kept on wondering why they kept on tripping on high or low levels. And because that valve had almost 7 or 8% hysteresis or backlash. So if you do have some backlash, what you could do is always use a bungee cord, just like we've shown you there, and kind of take up the slack of the control valve itself. Yeah, just kidding. Don't do that. Don't do that. I was just kidding there. I do not advocate the use of bungee cords to fix backlash in a control valve. So we're just trying to have a proof of concept that the backlash was actually causing variability in the gas flow in this example here. Stiction or static friction. Obviously, static friction can actually occur in many, many different places. So it can actually occur within the valve actuator, valve body. It can actually even live in the positioner. And what stiction means is that there's a lot of friction. Therefore, we tell it to move. There's too much friction. It's not going to want to move. And then you tell it to move a bit more, tell it to move more. And finally, you get a full change. And obviously that is going to have a very severe impact on our ability to control. And it does cycle in automatic as well. So I will show you that in a minute. But again, here I want to show you another video that I have. And I'll play that one there. So once again here, I'll set the stage here. So this is a large ball valve. This was actually done back in 2006, believe it or not. And what we did here, we were actually documenting. I was self-employed then, working for a customer. We were actually documenting the performance of control valves. This is a brand new mill, and these actual valves were all sticking and were causing significant production problems. And so we took one out. It's a pretty large ball valve. We actually had the actuator all tubed up with air, and we actually had a technician there with a 4-20 calibrator wired up to the positioner, and we're slowly opening up the valve as we go along. I'm not going to play the entire video, but you can see where the stiction actually occurs.
Go now. 4 milliamps. Go. Start opening it.
There's your fixture.
Just keep going. Open.
The actual little machine gun song you hear in the background is a positioner. And there you see the jumps. So I'll just pause it for a minute there. Obviously, we would like to see valve changes, the valve opening to be smooth and be able to track the 4-20 command signals we're actually issuing to the positioner. But you can see there's a lot of friction in this example here within the ball and the valve body itself.
That should be 50.
Okay, keep going.
There you see it again.
Yes. Okay, now go back the other way. Close it up again. Go slow. Go slow. Give me a couple percent every time.
They were actually closing. And it's definitely having a hard time.
I think there is a ramping function in there, right?
This guy.
Go on.
So a little bit more, and then we'll continue.
Close.
That's a great geyser.
Close.
And it seems to stick right around that position, if you notice.
Keep closing.
There you go.
Jump.
Yeah.
Close.
So some of you, I'm sure, have seen this type of videos. Often I've used them in different webinars and my courses as well. And this is actually sort of another simulated example, but it kind of shows you what stiction looks like. In this example here, I go up 1%, 1%, 1%, 1%, and finally I see a change in my flow. And had it been backlash, that means then for all of these bumps, I would have seen a change in my flow, but I didn't. And that's how I differentiate between backlash and stiction. And then when you put them in automatic, it will tend to oscillate. The output will be a triangular pattern, as you see there. And the PV will be sort of a shark fin pattern. And that's one of the things when I walk into a control room and I look around at all the trends, if I start seeing a triangular pattern on the output, that maybe, you know what, it could be a sign that valve is sticking. So how much is too much? First of all, if you have a control-related issue, there's a 30% chance the valve is involved. Okay? Backlash and stiction, no one said that they're mutually exclusive. No one said that they can't happen on Tuesday but not on Thursday. It can't happen at 50% open but not at 70% open. The idea here, fix the problem right at the situation. If you have a bad valve, fix the problem. Don't use bungee cords. Don't get too cute. Don't try to build a backlash compensator in software. Don't do that. Fix the problem at the source. Tuning will probably make things worse. Tuning cannot fix for a bad valve and probably make things worse in automatic than on manual. How much is too much? No more than 1%. No more than 1%. Now, when I first started doing this back in the late 80s, I'm not too sure how many of you were born in the late 80s, but when I started doing this, if I saw 1% precision, I was a very, very happy camper. Nowadays, I expect 0.5%. I expect 0.5%. Therefore, if I go up 0.5%, I want to see a change in my valve position. If I go down 0.5%, I want to see a change in a valve. I'd see a change in my valve position as well. And incidentally, a lot of times I like to do when I go in the field to check for the precision, if you can, obviously, if the valve is accessible and it's not too high, I actually like to put my fingers on the stem to feel either the rotary motion or the linear motion. And you get to gain a lot of insight as to how the valve is operating just by sensing how that valve stem is rotating or moving up and down. One thing, actually, there's an 𝗦𝗃 control valve dynamic specification. I put that in the handouts. A PDF, it's free. You can download if you want to. It's up to you. Where it will talk about the valve dynamics. How fast should it open for 5%, 1%, 10% bumps? It will talk about valve precision. It will talk about valve sizing. Actually, it's a pretty old specification, but still very, very relevant. I actually used to work for 𝗦𝗃 many years ago, and I'm really indebted to my mentor, Mr. 𝗩𝗚𝗙𝗢𝗕𝗦𝗧𝗔𝗬. With him and a lot of my colleagues, we developed this control valve dynamic specification. So we're kind of wrapping up here. Last chance at good control. Critical, the valve needs to be properly sized. Now, sometimes we try to ask too much about a control valve. You know, we want to control down at 10% range, and we want to be able to control at 80% range. Can we do that with one valve? Probably not very, very well. And maybe need to talk about doing a split range control, which is a subject of a future webinar. But really, properly sizing valves is very critical. Make sure that they get proper modulation, not over modulation, not under modulation. Remember, the lazy person's way of sizing a control valve is, if I got a 4-inch line, I'll put in a 4-inch valve. Dynamic, we need to be able to make sure that, you know, we can have all the properly sized, the properly precise valve, but if it takes 3 minutes for my valve to go from 20% open to 30% open, that's not very good either. So we need to have the valve dynamic to be able to get to its new position correctly and precisely as well. So there's 3 things that we need from a control valve: properly sized, properly be dynamic, and precise. So thank you very much for joining. My next session, it'll be June 16th. We're going to talk about level control and how improperly tuned level control can impact your process. So right now, I'm going to go to the question and answers. I think, Tim, you've been busy answering questions, have you not?
Yes, Sylvain, I've answered a couple of questions. The one question that I had, which I did answer, had to do with what defines the flow to open or flow to close design. And I tried to put that into words and in an answer, and hopefully it made sense to the person who asked it. But I guess just to reiterate, the flow passaging through the control valve and how the manufacturer designs his internal area, whether it's a linear up and down valve or a rotary valve, will determine when the flow goes through the orifice, whether or not at that particular point of opening, when the flow is going through, will it try to force the closure member or the actual element either open or closed. It's all based on dynamics of the flow going through. So it's more of a, it's based on the manufacturer and how he designs things. Because sometimes if we have flow going through a linear valve that's going up and down, some people may always think that that's, you know, the way the flow is going through the valve, it's actually pushing the plug up. But actually, depending on the design of the internals, we actually might have a tendency where when the flow goes through it, it might tend to close it. But okay. I guess the bottom line in all this is that the actuator that Sylvain spoke about early on has to have enough muscle to be able to resist whatever tendency is there.
Okay. I think also here, there may be a reference here to fail open or fail close as well. And therefore, so if you increase the 420 to close the valve, or you can increase the 420 to open the valve. And it depends on, and there's no right or wrong here, it depends on the application, where sometimes you might want the valve to be fail open, and sometimes you want the valve to be fail closed.
And there was a question that came in to Sylvain, and I thought I answered it, and when I answered it, the question disappeared. So I'm not sure if the person retracted the question or not, but it had to do with explain why equal percentage was favorable, the favorable characteristic for a control valve. And at the time when I was writing my answer to the person who asked it, I said, Sylvan's going through this right now, and I basically tried to answer it. And then I basically, at the end, I just said, bottom line is that we're, based on the varying pressure drop across the control valve, usually dictates that we're looking at an equal percentage characteristic for the valve. And obviously, I think Sylvan did a really good job of explaining that. So I'm hoping that individual got a clear understanding. If he didn't, certainly reach out to Lakeside and either Sylvan or myself or whoever you might deal with from an account management standpoint, and let's make sure we get that question answered.
Awesome. Yeah. Hopefully I did answer it. Again, I welcome your questions here. Feel free to ask any questions. We'll just pause here for a minute.
Well, we have one here. When replacing a valve and the CV curve is slightly different, is there a way to predict how we would tune our control system accordingly? Change in tuning parameters.
Yeah.
Okay, Sylvan, this is in your wheelhouse.
Thank you. And every time you change a control valve, especially if you change the sizing, change the type, you change the make, you're now affecting the process. You're changing the process, and therefore, yes, you definitely need to look at the tuning again. Can you predict? It's possible. If you're changing, especially a different type of valve, you may be able to actually predict what the change in the process will be, because the tuning must match the process itself. And if we can actually kind of predict, and it's possible, depending on the type of valve and sizing, it's possible then to be able to make your adjustments prior to putting the valve in service. But it's always advisable, anytime you make a component change, even just changing a positioner. Tim and I have seen that on control valves where the valve itself didn't change. We just put a new positioner on there, and that changed the dynamics of the valve, changed the dynamics of the process, and we had to go and retune it. So unfortunately, it was, in this example here, was a nuclear power plant, and they don't allow you to change tuning. So we had to do other things instead. The other question I have, Tim, do you have anything to add to that?
No, I think you've nailed it, Sylvan. And I guess the key thing there is if you've got an old valve in there with potentially higher friction than a new valve that might be going in, or a positioner that's quicker responding, those P&ID parameters that you got in there might actually make things a little bit more exciting when you put in that new valve or new positioner. So yes,
correct.
Most definitely.
I actually remember that it was my second day at Lakeside. If you remember, Tim, you and I, we went to this power plant, and they were having issues. We put in some brand new Fisher control valves, and they're having control issues. And when I looked at the tuning, the PID tuning of these, I think it was steam flow, if I'm not mistaken, or steam pressure. The issue was that the tuning was matched to the older valves that were there, and the older valves were very slow, sluggish, and therefore the PID tuning had to be more aggressive to overcome that sluggishness in the valves. And then we replaced them with our valves, and who are very responsive, and now that was actually affecting the controls. And again, there's an example where we had to actually change the tuning because we changed the valves, process changed, and therefore we had to change the tuning. Another question here: how do you distinguish between response time and stiction? And I guess what the person's trying to tell me here is, let's say we have a pH control where we're adding caustic, but there has to be a bit of time delay, process time delay, between the moment you inject your caustic, let's say, and the moment you measure your pH, because a chemical neutralization has to happen. Now, how do you distinguish between? You have to sort of imagine, kind of, I tell people to be in the pipe, is that in the sense that you say, well, based on this control loop, I expect that there should be about 10 seconds of time delay for this process. Now, if you look at a flow, let's say a liquid flow, and I open up the valve, I shouldn't be waiting 10 seconds for the flow to increase because it's an incompressible fluid. So there, if I tell the valve to open, but then my flow opened up, let's say 10 seconds later, that's an indication maybe I got some friction in my valve and the valve's having a hard time opening when I tell it to open. Next question is, other than sticky valves, are there causes of cycle in the loop, such as cycle from upstream process? How do we tell this from the real cause? Very good question. Very good question. So I'll rephrase the question a little bit. So if I see some oscillations in my control loop, and then how do I know it's not caused by an external disturbance as opposed to possibly caused by that sticky control valve? And the way I do that usually is that I would put that control loop in manual. The one that I suspect is actually causing that oscillation, I would put it in manual at a fixed valve position. And if the cycle disappears, then I know that that valve or that control loop is the problem. If the cycle still persists, then I know that it's something upstream, downstream, or sideways that's causing that. One last thing I want to emphasize too, maybe Tim, you can have you ever seen a control valve move while in manual mode?
In my history with looking at this sort of thing, I mean, that would only be attributed to the fact that maybe you've got an undersized or a weak actuator, and the flow, going back to that first question that the person asked earlier about, does the flow tend to want to open or close the valve? And that would be a scenario where, you know, you've got the valve in manual, and then all of a sudden you can actually physically see or tell that the valve is moving. Then that could be an actuator that is actually just too weak and can't hold the closure member or the element that's moving. It can't hold it in its position. So
correct,
it could
yeah,
be related to some sort of flow disturbances or dynamics that are causing that.
yeah. And I've seen that actually on large butterfly valves where there's a lot of forces on that disc and a lot of torque, and that poor old actuator and positioner was having a hard time keeping that valve in place. So, all right, another question here. For high differential pressure liquid applications, which cavitation might be possible? Is always a globe valve the first choice? That is one thing we have to understand here, and I'll pass it on to you, Tim, in a minute. But one thing we have to understand here is that valves are highly engineered products in the sense that, you know, we could say control valve is the same, but really the control valve is matched to the operating and process conditions you give us. And so to say that a globe valve is the first choice may or may not be true, but cavitation can happen. Now, for those of you who don't know what cavitation is that as the fluid, a liquid passes through the smaller opening, the liquid will accelerate. And Mr. Bernoulli said back in the 1700s that the pressure times the velocity of a fluid must remain constant. And so what happens as the fluid accelerates towards that smaller opening, the pressure will drop. And if the pressure drops below the vapor pressure of that liquid, it will actually boil into a gas. And then as the fluid continues to move forward, it will slow down. The pressure will increase. That then boiled gas will actually collapse and will actually impinge on the valve body and cause a lot of damage. And it sounds like gravel or rocks flowing through your through the valve. But back to here, Tim, is globe valve a first choice to talk when we talk about cavitation?
Not necessarily, but it's sometimes, usually that's where we'll end up. But the bottom line with this whole thing, and Sylvain explained it perfectly, what happens when you get cavitation through a control valve. The key to preventing cavitation is staging the pressure drop through the control valve in such a way that you do not get to a point within the control valve cavity where the pressure drops below the vapor pressure. So whichever valve design you decide to go with, whether it is a globe or a rotary valve, you need to ensure that at the vena contracta, which is where this magic happens, that the pressure at that point does not get below the vapor pressure. So staging the pressure drop is key. And in some cases where we are dealing with a high pressure differential across the control valve, I mean, globe valves are obviously where we end up, but not necessarily. Sometimes we can get away with looking at other choices. But bottom line is picking the valve that will do the staging correctly is the key.
Okay, awesome. All right, we've got a few more questions. Is backlash fairly common on linear actuated control valves or typically more issue on a rotary? That's a very good question. I would tend to say, depending on how it's assembled, but definitely I would say that it's likely more common on rotary actuated valves than linear actuated valves. Next question is, sometimes the required CV at maximum case dictates the valve size that may look oversized for the normal operating condition. How could oversizing be prevented in such cases? Very good question. And the answer there is, if, again, remember, I think I said at the end that maybe sometimes we ask too much of our control valve, that it needs to operate at the very high end, but maybe oversized at the normal flow rate. You may want to consider dual valves in parallel to be able to have a better turn down ratio, modulation range, and still stay within the sweet spot of the control valve. So you probably need to look at two valves in parallel and split range them. And again, we're going to talk about split ranging in the future webinar. Another question here is, for level control valves with no upstream pumps, is equal percentage characteristic an incorrect choice? Another very good question. So here, if you're thinking you got a tank and you're controlling the level by the discharge, your gravity discharging the tank into another tank, let's say, where the P1, the actual static head pressure on that valve, is constant because I'm actually maintaining that level, probably a butterfly valve, because now my DP will be constant throughout the range, perhaps a butterfly valve would be a better choice because it has a linear CV characteristic. So, and then the last question, it is very dependent on pressure and the recovery factors of the valve design. I guess someone here is just trying to
That was an internal, yeah, that was an internal comment about going back to the cavitation question.
Exactly that. I know we passed our 1 hour mark. Is there any more questions? I'll pause for a minute, and otherwise, definitely want to thank you. I'll pause another about 30 seconds, see if there's any other additional questions.
I think everybody ran to lunch, Sylvain. We're down to 12.
So.
We're down to 12 attendees, so
okay.
Everybody wanted to get their hamburger and fries.
You got it. Well, for those remaining, thank you very much for attending. Very much appreciated. And as always, feel free to reach out to us should you have any additional questions. So I'm going to end the webinar now, and thank you very much. And as Albert Einstein said, imagination is more important than intelligence. Thank you.